Assalamu alaikum everyone. Starting with the name of Allah. My name is Ashir Mumtaz and this was our project. We were given a project in which we have to made a PCB on a H-bridge motor, a DC motor that can rotate on both direction. It was our project of the final semester of second semester. So we created a project. The name of the project was DC motor controlled H-bridge because the motor in the project was a DC motor which was controlled by the H-bridge. In this H-bridge we put four diodes and created a H-bridge. These were our group members: Muhammad Usama, Ashir Mumtaz, me and Wasi Heather. And our instructors was Dr. Umar Farooq, Sir Muzammal Ghaffar. So let's talk about the overview of our project. The object of the project is to design and implement a BJT controlled bi-junction transistor controlled or JFETs controlled H-bridge circuits with the capability of controlling whichever direction a DC motor of our choice will rotate. So we were given a task to rotate the DC motor in both directions, left and right, by a switch. So DC motor of our choice, also known as bi-directional control, in which we can control it in left and right direction. Both directions of the operation for the motors are controlled by two switches acting in the cohesion to achieve the objective, and by that it is understood that if both switches are turned either on or off, the DC motor should not activate. As we know that the H-bridge, if both diodes are connected, the H-bridge will not run. So if the both switches are on or either off, our motor will not rotate. If either of the switches are on or other is off, then the circuit should function in a predictable manner under the parameters set by the designer. So if we turn on one switch, our motor will rotate in that direction in which we have controlled the direction of that switch. In addition, it has been required that the motor runs at 9 volts and draw a minimum current of 2 amperes. With that, it is also mandatory for us to implement the functionality of the optocouplers PC817 within the circuit and the integrate flyback diodes. So let's talk about the autocouplers. Autocouplers is the component that we used in our PCB. Optocoupler works. Optocoupler, there is a LED in the optocoupler. When the current passes through the LED, so the LED blinks. This LED helps the optocouplers to pass the current through it. So when the LED turns on, it becomes conductor, so the current can pass through the optocoupler. Furthermore, the circuit should operate for at least 15 minutes. So we tested our circuit. Our circuit will at least run 15 minutes. The following contact will provided a detailed description and analysis of our H-bridge directional motor control using BJTs as a switch. So these are the components or material that we used in our project: TIP31 and TIP32. TIP31 and TIP32 are transistors, which were TIP31 are PNP transistor and TIP32 are NPN transistor. So two terminal T blocks. We put T blocks so we can connect our battery with the output, and DC motor with the output. PCB board, which was necessary to make the H-bridge PCB, was the first thing that we need to create this project. Push button or any other type of button. We can use any type of button for this project. Resistor, we put 4 resistors in our project. PC817, which was optocoupler, IN4001, which were diode to make a H bridge, and DC motor to run the circuit. So these are the list of our material that we use in our project. We use 4 TIP, 2 TIP2, 2 terminal T blocks, 1 PCB, 2 push button, 8 resistor, 2 PC817 means 2 optocoupler, 4 diodes and 1 DC motor. So here is the working principle of our project. H-bridge is a specific type of formation of BJTs that enable the circuits along with its input parameters to control the direction of the rotation for an electrical motor actation as the LED. The controlling of the switches, push buttons, is a core function. It determines in distant way to operate the motors. When BJTs are active, as prototyped in the following figure, the current should travel along the terminal of the motors accordingly. We can see in this diagram, if we turn on the side A, means we turn on the A side push buttons, the current will flow in that direction. It will pass through the optocouplers and from the H bridge, then the motor will turn on and the current go to the ground. In this way the current will flow if we turn on the A switch. Similarly, recalling the necessary implement of the PC81 optocoupler, it would serve the purpose of the H-bridge designs only if its activation is enabled in this way figure demonstrate. So we can see the board diagram. If we switch turn on the B side, then the current will flow in this direction, V side, then with autocoupler of left side autocoupler, and then from within through the DC motor to the ground. Both circuit in a circuit there are two circuits. One circuit that rotate the motor to left side and other circuit that rotate the motor from right side, but they are implemented in a single circuit. So it is necessary to have the manual switches control to flow the optocouplers, and if it activates, then the current should process in its path to activate the BJTs. If the optocouplers is not activated due to the state of manual switches, the circuit should not operate. If the both switches are off or both switches are on, the circuit will not operate, because if A and B are on, then the circuit will not move. The current will neither flow through the A side or not from the B side. This is the theory of our project. It's based upon true or false really. If switch 1 is on with question 4, Q4 means that Q1 is on, that optocoupler is on, and Q4 is on, and that autocoupler means that diode is on, then the current flow through this clockwise direction. Here we can see if Q1 and the Q4 are on, then the motor will rotate in clockwise direction. Similarly, if the Q3 and Q2 are on, as we can see Q3 and Q2 are on, the current will move the motor will move counterclockwise, mean anti-clockwise. If both Q1 are on, if all the transistors are on, or neither all the transistors are off, the current will not flow through the circuit, which means motor will not turn on or motor will not rotate. In each condition, the circuit operates accordingly to the parameters case Q1 plus Q4 or case Q2 plus Q3. According to the data sheet of the each transistor that is instant to active, a specific amount of base current must be provided for the transistor to allow the current to flow into the motor. For either combination, one has a higher signal activation, the transistor also known as on state, while the other two transistors will have a low signal and therefore be in the off state. case 2, if all are on or off, if both switches are on. Visualizing a mirror design on each side of the transistor were enabled. High signal would meet at the center where the motor is effectively cancelling each other and rendering the circuit inactive. If they are off, then the optocoupler in change of supplying current to the resistor in order for activation do not receive current manually, meaning the phototransistor does not return on. If we look at this diagram, if we turn on both switches, this current will flow in this direction and this current will flow in this direction. So the both current cancel the effect of current each other, so the circuit will not on if the both switches are on or the both switches are off. Here we can see it clearly. The addition of flyback diode is an effect because of the high voltage rise across the transistor when they are instantaneously turning on or off, generating heat within their terminal and reducing its function in the long term. This high voltage that generate is called back EMF or flyback voltage, and therefore the diodes are flyback diodes. So we can see here it is moving in that direction. So now there is the concept of PNP and NPN. When both NPNs and PNPs are emitter current IE is the sum of the collector current IC and base current IB, represented as IE is equal to IB plus IC. We can see their diagram and symbols. However, in case of NPNs, their emitters emit current and the collector base retrieves current PNP collecting current from their emitter and distribute current with their emitter and base. We can see the PNP and NPN symbols in which the emitter is downward direction, while in case of PNP the emitter is into the base. So why uses PNP? There is always a question, why uses PNP? One reason is that PNP saturates with a voltage loss of 0.2, whereas with NPNs it can vary between 0.7 to 1.5. Having it on the high side lower the voltage and thereby optimize the voltage supply to the DC power motor. It is especially effective when working with low voltage source. If the alternative is used, then there will be manually voltage supplies to the load. You can also supply more voltage with the PNP type transistor supply. Suppose if your motor needs 10 volts DC volts, you cannot connect a 7 volt to the emitted pin of PNP transistor and specific output which has 3 volt to the base pin of PNP transistor. At the end you will have 10 volt DC voltage at the collector pin. As for the motor, we have adjusted our circuit to fit the requirements for two different types, each with a large distant level of coil resistance and torque. This can be achieved with slight tweak in the resistance value throughout the circuit and in accordance with this transistor. In case of motor with the lower coils resistance, lower value resistance are used throughout the circuit to ensure that higher value of current emerge from our set voltage ensure. Similarly, if we want the motors with a higher coil resistance to operate, it would be required to increase the resistance throughout the circuits in order to produce lower amps so as to generate the same desired voltage across the motor. So here is the block description. The block description similarly portrays the order of functionality of the circuit, starting with the activation or supply of the battery When it turns it allowed by way of push buttons present in its path. Following activation, the supply actually the path through the H bridge and it consequences pass through the motor, which also activates in accordance with the level of supplies. So now we talk about the components we used. The first and the most important components of our PCB was the DC motor. The initial design for a motor of a high level of coil resistance, allowing minimal current to pass through the BJTs and in turn activate the motors. The specific motor with a nominal voltage of 6, high torque with a high RPM of approximately 9000 was relatively easy to activate, as even a current of 36.6 milliamps as shown in the schematics of page X. Passing through it was enough to power its voltage of 10 volt. The advantages of using TIP transistor was thoroughly explored with the required adjustment was made to accommodate the supply for a lower coil resistance motor in contrast with the specific motor having approximately 200. So this is another type of motor. With a few adjustments in resistor throughout the circuits along their arrangement, we will able to integrate a 9 volt geared DC motor operating with a relatively high RPM but significantly lower coil, 3.5 to be praised. The heavy duty motor requires at the very at least 1 amps to operate at satisfactory level, with we were made possible through the dynamic scope of tip. So it was the main point which motor we used for our project. This motor was a small motor, but it can rotate in only one direction. So we used that motor, which is a high duty motor and required 1 amps to operate a satisfactory level, which can handle current. In addition, high voltage, especially when directly received from the source of PNPs, do in the low resistance motor design. The other thing was rectifier. A rectifier is an electrical device that convert an alternative current, AC current, to a DC current, typically used when we are concentrating a current with component that required the transformation in order to function and avoid damages. Its formation is comparable to one-way value, which only allows current to flow in one direction, thereby converting AC current to DC. In this specific video, we have not implemented a rectifying device of any kind of the supply to the DC motor. Voltage regulator. Voltage regulator is a measuring of the stability of the secondary voltage supply by a power transmitter. When it receives a constant primary supply voltage, this is measured in percentage, and the lower it is, the more stable it is. The most stable in the output of the transformer, and in consequence act in coherence with the component attached to the rest of the configuration, since it is likely that they will be more sensitive to voltage and current fluctuation. In the specific configuration, there was no use for a voltage regulator or a power transformer of any kind, so it was not implemented. So here we can see the schematics of our PCB. Here we put the battery of 12 volt. For PCB layout we put key blocks. Here is the switch. The PCB of the PCB component of the switch was not given, so here we also put a T block. There we put two resistors. It is auto couplers. When the current pass through this resistor, the LED turn on, so it allows the current to pass through this way. So the current will pass through this way, and then from emitter to this resistor, and then from transistor to the motor. So there is 4 diodes, D1, D2, D3 and D4, which was making an H bridge. This circuit is the mirror of this circuit. These two circuits are same but operates inversely. If we turn on switch 2, the current will pass through in this direction and the circuit will move DC motor will move clockwise. If we turn on that switch, the current will flow through this and the DC motor will move that side. There are the values of the amps and the motor. With that, here is the T block, because the motor PCB layout of the motor was not given, so we put T block for this. Here is the calculation of the primary supply current 1.6 ohm, emitter current which was PNP 1.5 amperes, collector current PNP and NPN 1.46, base current 88.7 milliampere, base current of Q1 2.40, and for Q4 it was 9.1. Motor current was 1.46, which was pretty good. Voltage current 8.74 volts. So here is the PCB process, that how we create our PCB. First we get the data sheet of each component of the configuration. Then we tested the configuration on the breadboard. Then we designed our PCB in according with the schematic along this spatial spectral optimization. Gathered the print and implement the design on the breadboard. After that we remove the copper by mixing the chemical into the water. In a hot water, the copper move from the access side and remain intact on that side which the PCB was printed. After that we drilled the holes in which we have to put our components. We drill the hole and then put our components accordingly with our schematic. After that we sold the component and then we sold the component and fixed all the components. It was the process of PCB, and here is the view of our PCB which we printed and put it into our circuit. Here was the name was given. It was the PCB design of our circuit. Here is the 3D view of our circuit, that how our circuit looks in a 3D view. You can see. Now talk about the automated H bridge, which was also the part of the presentation. So what is automatic test bridge? We can see the automatic test bridge circuit. The circuit is pretty similar to that circuit we used for our simple H bridge, but there are some changes in this circuit. You can see that code behind it. There is logic of the LEDs that turn on the autocouplers. This code is the logics that makes the logic of that our previous design. It is the previous design of our schematic project, and this is the automatic PCB of our circuit. Here we can see there is 2 optocouplers from that side and 2 optocouplers from that side. 4 resistor and the transistor increase accordingly. So it means there are 3 switches, 3 LEDs and 4 autocouplers, but it work on the same process. This code helps the circuits to run. With the help of this circuit, the code run and the PCB start to running. In this code there is a logic of the loops. We can see there is a while loop in this principal logic which helps the circuit to run. We use 2 libraries, int PU and this kind of things. Here is our previous design. So here is the, we can see the automatic of our PCB. This is the automated PCB which runs on the code, and this is the 3D view of our circuit, how our circuit looks. That So let's talk about the problems we faced during the making of our PCB. What was our problem we faced during the PCB? So the biggest problems we faced during our PCB was the dry soldering. It was difficult to troubleshoot the circuit when it is grated completely but it is not turning on. So what we can do is to troubleshoot that circuit. So start with the soldering. We see many components that were sold dried. From that soldering, the current was not passing through that components. It means that the current passing through that component will stop because it was dry soldered, so the current backward move. So it was the first and the biggest problem we faced in every type of project. Second, we face the problem of breaking the circuit. When we drill the circuit breaks and the path of the circuits break, from which the current the circuit become open and the current do not pass through the flow. So what we do for this problem, we attached the soldering wire with the breaking path. So we created a path, in this way the current flow through that path. And other was the short circuit. The soldering, sometimes the soldering touch with each other. The component was, if the component are too close with each other, when we solder the component, the soldering touch to each other. At that case, the circuit becomes short circuit. So the current pass through the whole circuit, in which the circuit don't run. So we think that our circuit is flawed. So what we can do for this problem, we took a sandpaper and tried to remove the excess of wires from that side. If the circuit is becoming short, so we remove the circuit from where the circuit is becoming short. So these are the problem we faced on our project. Now we see the picture of our project. Here we can see the original image of our circuit. This is the upside of our circuit. These are the two push buttons. This T block is for input. These four diodes are making edge bridge. These two are autocouplers and these are transistor. There are some resistor, and this T block is for output, where we put our motor. This is the back side of the circuit. You can see the path and the name written here. You can see the path from some side. There we break our circuit, so we solder with each other to make a path for the current to flow through it. These are the buttons. So this is the soldering, and this is the original image of our circuit. In the last, we talk about our expense on this project. So we used two PNP transistor, that was TIP32, that cost about around 17 rupees for both, and 4 PNPs, it is about 140, because the price of the PNP and NPN are same, so it was greater in quantity, so we spend 140 rupees on this. We spend 6 rupees on 6 transistors, because each transistor 1 rupee. So the most costly thing in our project was the 9-volt DC motor, because it was a high duty motor which can rotate both sides. So we used T block, that was 20 rupees for each, so it become 40 rupees. We used 2 push buttons, that was for 100 rupees. Fiber board 500 rupees, breadboard 250, diodes 80, optocouplers 40, and the PCB print in about 100. So we spent about 1850 rupees on our project, and there are some costs of the project. So here are the references links from where we get the data sheets of the TIP 32, TIP 31, PCB 817 and IN 4001. These are the references link from where we get the data sheet of these components and try to make our circuit accurately. So that is it for today. Thank you. I hope that you liked our presentation. Allah Hafiz.